As I'm recording this audio, my microphone is detecting changes in air pressure over small time intervals, and the software is storing the data it receives from the microphone. If I then save this audio as a .wav file, the data that is written to my drive would be exactly the data from the microphone without processing. For many purposes, this works great, but when it comes time to do something with this audio file, like send it over the internet, we start to worry about file size. Maybe I don't need to store the exact data from the microphone. Maybe we can do something more clever to get a smaller file. This is where audio compression comes in. There are clever ways to transform or encode an audio file into a smaller one. For our purposes, there are two ways to compress audio. The first is to ensure that all of the information of the original audio file is preserved. This is the approach taken by the FLAC format, for example. The second is where we focus on making the audio file as small as possible, while still sounding close to the original file. This is the approach taken by the MP3 format. The first type is called lossless encoding, because it doesn't lose any information. The second is called lossy encoding, because it loses information. Of course, because it doesn't lose information, we can't guarantee that FLAC will reduce the file size. But we gain a benefit from this. I could take an FLAC file and turn it back into the original .wav file. With an MP3 file, I know that my file size is going to shrink, but I can't guarantee that I can retrieve the original audio. In fact, most of the time this will be impossible. Let's represent this idea mathematically. Take any encoding that is guaranteed to shrink file size. So it takes a file of size n bits and returns a smaller file of size m bits. Then take any decoding procedure that takes an encoded file and outputs a file of the original size. Then it's always the case that there exists a file such that if we encode it and then decode that encoding, we don't get the original file back. This principle is called lossy code. From a computational complexity perspective, we like to phrase principles like these as total search problems. That is, given what we call an instance of this principle, in our case, an encoding procedure and a decoding procedure, we search for an input that witnesses the principle. In our case, a file that can't be encoded and decoded correctly. A search problem is total if every instance has such an input. And because we know that the principle behind lossy code is true, lossy code is total. Lossy code is also what we call an NP search problem. That means that if we find an input that is a solution to the search problem, we can efficiently verify it. Given any file, we can encode and decode it and see if it changed. So it belongs to the class TFNP, which is the set of total search problems that are efficiently verifiable. In fact, lossy code has an even stronger property. It can be solved via an efficient random procedure. If I randomly choose a file, odds are that it will be a valid solution. Encoding it and decoding it will give us a different file. So it belongs to the class TFZPP, which is the set of TFNP problems which can be solved with randomness. My name is Morgan, and I wrote a paper about TFZPP with my friends Noah, Stefan, Sid, Jiaowei, Hanlin, and Wei Qiang. It's called Total Search Problems in ZPP, and it will appear at ITCS 2026. You can read the paper on ECCC or arXiv. In this video, I'll give a brief overview of our results and some ideas about how we proved them. I'll start by talking about some basic properties of TFZPP. Then we'll take a look at what types of search problems are in TFZPP. We're particularly interested in how hard problems in TFZPP are compared to lossy code, because lossy code is a problem people care about in the literature. We showed that there are problems in TFZPP that are much harder than lossy code. These problems are pretty complicated. Are there any simple, easy-to-describe problems in TFZPP that are harder than lossy code? This is still an open question, but we give a candidate called nephew. On the other hand, a lot of other problems that you might come up with turn out to be equivalent in difficulty to lossy code. Specifically, we studied the query complexity version of TFZPP. This means that the cost of a protocol is measured in the number of bits that we need to look at from the instance. So for lossy code, an efficient protocol couldn't look at the whole truth table of the encoding and decoding functions. Instead, we can evaluate the encoding and decoding functions for a small number of files. This is what I meant when I said that the random protocol for lossy code was efficient. randomly choose a file, encode it, this is one evaluation, and decode it, that's another evaluation, for a total of 2 evaluations, and 2 is pretty small. I'm going to write a little DT, which stands for decision tree, above the classes here to remind us that we're talking about query complexity. When we compare 2 search problems, we want to know if we can efficiently transform an instance of one into an instance of the other. This is called a reduction. A problem P is equivalent in difficulty to a problem Q if there's a reduction from P to Q and also one from Q to P. Q is harder than P if P can be reduced to Q, but Q can't be reduced to P. For the exact notion of reduction we use, please check out the paper. Now on to the results. We first proved that TF-ZPP is characterized by the proof system randomized tree-like resolution. This connection is a tool we will use later. A proof system, or to be more precise, a propositional proof system, is a set of rules that can be used to prove that an unsatisfiable CNF formula is unsatisfiable. The length of a proof in a propositional proof system is how many times the rules are used. The goal of proof complexity is to find short proofs or to prove that no short proofs exist. For any unsatisfiable CNF formula, we have a corresponding false clause search problem where, given an assignment to the variables of the CNF, we try to find a clause that is made false. Because the formula is unsatisfiable, such a clause must exist, so this problem is total. Because it's easy to check if a clause is false given an assignment of variables, the false clause search problem is in TFNP. So what do we mean when we say that some subclass of TFNP, in this case TF-ZPP, is characterized by a proof system, in this case randomized resolution? It means that the false clause search problem for some formula is in that subclass if and only if there's a short proof in the proof system that the formula is unsatisfiable. So our theorem means that a formula has a short randomized tree-like resolution proof if and only if its false clause search problem has an efficient randomized protocol. We use this characterization to prove separations between TF-ZPP and other TFNP classes. First, under an assumption, we separate TF-ZPP from all uniformly generated TFNP subclasses. See the paper for the full definition of uniformly generated, but you can think of this as any standard TFNP class that you might have heard of before, like PLS, PPP, or PPA. Specifically, we prove that TF-ZPP is not contained in any uniformly generated TFNP subclass, assuming that Boolean satisfiability has no quasi-polytime algorithm. Or, stated in terms of complexity classes, NP is not contained in QP. And note I don't use the DT superscript here, so I really mean the classical complexity versions of these classes. We think this assumption is true, so that's good evidence of a separation. We get this result using a theorem of Pudlak and Thapin. They showed that, under the assumption NP not contained in QP, there are unsatisfiable CNF formulas that have short randomized tree-like resolution proofs, but have no short proofs in any non-randomized proof system. TF-ZPP is characterized by randomized resolution, and every uniformly generated TFNP class is characterized by a non-randomized proof system, by the result of Buss, Fleming, and Impagliazzo. So, using the characterizations, our theorem follows directly from theirs. We also give a separation that does not depend on any unproven assumptions between TF-ZPP and the standard classes PLS and PPP. For all of these separations, the TF-ZPP problem demonstrating the separation is sort of tailor-made to show the separation. We wouldn't expect anyone to study these problems in their own right. Can we find an easy-to-state problem where we can prove a good separation? As a starting point, can we separate any easy-to-state TF-ZPP problem from lossy code? Our main candidate for such a separation is a problem we call the nephew problem. Given a set of vertices and 2 functions, f and g, find a vertex v, where starting at v and applying g, then f gets to a different vertex than starting at v and applying f, or starting at v and applying g and then f gets us back to v. Let's take a moment to think about this definition. Suppose a vertex does not match solution type 1. Then we could get a structure that looks like this. Follow g, then f, and we get to the same place as following f. Or we could get a structure that looks like this. Follow g, then f, and we get back to the original vertex, and then follow F again, and of course we got the same place as following just F. But now this second structure matches solution type 2. Following G and then F gets back to the original vertex. A third structure could be if we have a vertex that points to itself with G, then points to a different vertex with F, but that vertex points to itself with F. Then this is not a solution because G then F gets to the same place as just F, and G then F gets us to a different place than where we started with. So these are the two possible local structures around a vertex that is not a solution. The name nephew comes from the first structure. If we think of F as pointing to your parent vertex, then this is your sibling because they have the same parent as you do. And this vertex, the one pointed to by G, is your nephew, or niece, or nibbling, but I don't think that word is very widely used. So nephew is in TF-ZPP, but possibly it's not immediately clear why. To show that it's total, let's look at the graph formed by just the F arrows. This is a graph without degree 1, and a basic graph theory fact is that such a graph is a group of cycles, and trees pointing towards those cycles. Assign each vertex a level that shows how far away it is from a cycle. Okay, assume that there are no solutions. Then we can show that there is a vertex of level at least 2. In fact, follow G from any of the cycle vertices, and you get to a vertex of level 2. Then from any vertex of level L, which is at least 2, its local neighborhood looks like this first structure we saw before. In this structure, following G arrives at a vertex 1 level up. So if there are no solutions, we can keep finding vertices of higher and higher levels, which is impossible in a finite graph. Okay, now, why does it have an easy randomized protocol? This one's a bit more complicated, but the basic idea is that we can create a binary tree using the structure of a nephew instance. For each vertex, create its left and right children by following G, this is the left child, and then following F and then G, this is the right child. And then a vertex is a leaf if it's a solution. I'm sweeping some details under the rug here. We end up with a binary tree, and then walking down a binary tree is likely to find a leaf, and therefore a solution, in logarithmically many steps. The idea of walking randomly in a binary tree and finding a solution is interesting, so we studied it. We introduce a problem empty child, where we have a binary tree and try to find a leaf. This problem turns out to be equivalent to lossy code in terms of reductions. And the proof of this is quite involved. I'd invite you to read the paper if you're interested. We also present some more results on the relationship between lossy code and other problems in TF-ZPP. As an example, we showed that the following problem capturing the AM-GM inequality is equivalent to lossy code. The input consists of a coloring function C that assigns the integers between 1 and 2n to one of two colors, and two mappings, F and G, from a pair of integers in the range 1 to 2n to an integer in the range 1 to 1.01 times n squared, and back. F is claimed to map specifically to the subset of these pairs where the first element is color 0 and the second element is color 1. Our goal is to find a number x such that applying G and F doesn't get you back to x, or an x where the promise on our input is violated. This problem is total because of the AM-GM inequality. If A is the number of elements in the range 2n that are colored 0, and B is the number of such elements colored 1, then A times B is less than n squared. So a random pigeon in the range 1.01 times n squared should have a constant probability of being an answer. If this problem sounds interesting to you, please pause for a minute and think about how to reduce this problem to lossy code. Okay, so one part of the solution looks a lot like lossy code, but it's unclear why the second part of the solution, where we enforce the promise on F, should be related to lossy code at all. It turns out to be a highly non-trivial task. The reduction to lossy code is obtained by formalizing the totality of this problem inside the bounded arithmetic theory APC1, using the machineries developed by Emil Ježabek. We also show that a problem corresponding to the dense linear ordering principle reduces to lossy code. If you want to see more details, you're welcome to look at our paper. Okay, so that was a whirlwind tour through total search problems in ZPP. I hope you enjoyed it, and thanks for joining me.